The other video is still processing in the background because it's an hour long. I hate these very long videos. So this is the software half. It's actually more slides. I think there are 50 slides. I'll try to get through them more quickly. Ignore the stuff that I don't think is important. Not saying ignore it, but you don't have to listen to me talk about it. And what was the other? And not have as many tangents. So let's see how this goes. So software is just the general term. It's the stuff that actually does the logic computations and stuff on top of the hardware we just got through talking about, right? And I was about to say there are mainly two types, and this is what this slide says. I almost just ignored this slide, but there's system software, OS and stuff, and there's application software. And the line can be blurry between these two. Again, it's like a spectrum. You've got, one side of the rainbow is red, the other side is purple, right, violet. Where's the line between the two? Sometimes that's kind of hard to see, but there's some things that are definitely red here, like the OS, the kernel, for instance. That's definitely system software, no question about it. And let's say Word, Microsoft Word's definitely application software, but there could be things in between, for instance, the window manager in Linux. Is that operating system or is that application really? It gets a little hazier. So, and I think that's why they have the word middleware in here too. But we'll talk about what these things mean as we go through these slides. Let me get rid of my YouTube video so then we'll start playing. All right, so let's see if any of this stuff's important, or you can just read it. So who all's using the software, whether it's just individual users, groups of users, a whole company, whatever. Work groups, that could be like a team somewhere, and then the enterprise, like everybody uses this database system at this company, right? Or everybody uses this to record their time. Everybody uses Brightspace. When I say record their time, I mean like clock in, clock out, that kind of thing. All right, so this slide you can just look at. I'm not really even look at it. It's just talking about different things. I want to get into the discussion about operating systems versus stuff that's not, and all that stuff, because there's some things I wanted to point out. I know the slides don't really talk about, so in the reading. I should have just gone through the reading actually, but it's very similar. This is covers the same material. So single computer, single user, that's like your desktop, and then you can have a single computer with multiple. All right, so obviously this stuff's just like obvious, so we won't belabor it too much. Sorry, I ate cucumbers today, so on a sandwich, so I have to pause every once in a while. Okay, so operating system. So operating system, let me stop. I don't like the definitions that they have here aren't wrong. I just want to there's a way to define an operating system that I really like, that I haven't seen used here. Let's see, I've got this. I meant to add more terms to this already, but I've only got this one ASCII stuff. But an operating system. I can't resist. Opus opera. This means work, or the plural is works in Latin. So it's anything that operating is something that's working. That's what the word comes from. So his magnum opus, his big work, right? Or opera. For some reason, I guess they use the plural of works to describe, the singing things. But anyway, an operating system is something that performs work. But the definition I want to give you for an operating system for computers is, this is one aspect of it. I think it's probably the most important job, but you could debate that. But a broker of system resources. So sometimes people will define an operating system this way, which is not incorrect, but it's the software that it exists between the user and the hardware, and that's one way of doing it, describing it. And it's true, but I like the word broker, because an operating system, and they don't really stress this on any of the slides that I've seen, But an operating system is, I want to get back to our slides and I've lost them. Okay, here are the slides. The slide we're on. Let's do F5. I guess I just have to move this out of the way, actually. There we go. An operating system is a broker of resources. So resources would be things like, the most important resource is the CPU. Main memories are a hardware resource. Let me get this off the screen now. Okay. Main memories are hardware resource, your disk drives, stuff that's hooked up to your computer, the buses and the network cards and the, what else? I guess you could say the display. Yeah, that counts. Keyboard, mouse, all these things that are hooked up to your computer are hardware resources. And it's possible, especially these days, we talked about multiple processing before. Remember that? Multi-processor computer. It can run more than one program at once. I should define that too real quick. You don't have to necessarily remember this, but I think it's a useful concept, and that's a program is a set of instructions. It's an algorithm that a computer can understand and execute, can perform. That's a program. A process is a running instance of a program. So when you launch a program, usually in the form of an application, it's running in memory. That's a process. You could have several processes of the same program running on one computer, especially if you got multi-core and all that, but also just one core, you can juggle time in between the different and give the illusion that they're all running at the same time when they're not. They're just switching out very quickly. More quickly than you can imagine and understand, really, as a human being. But if you've got multi-processing going on, more than one process could want to use the same resource at the same time. So two different processes, like say Word and Notepad, just a real simple example. You've got something you've written up in both, and you hit print at the same time, or close to the same time. Your operating system ultimately is what decides which thing goes first or how much time each thing. The operating system actually is the thing that decides how the operating system is implemented in regard to the CPU, is the thing that decides how much time each process gets before it has to switch with the other one or the other ones. Like you have 1,000 processes running at once, really. It's the thing that determines what thing can talk over the network, or whose bytes get to go next, and then pause this one for a split second while this one sends some bytes, that kind of thing. It's the broker. It brokers the resources. Broker is the thing that determines a broker handles resources in real life, right? It says this goes here, this goes there, that goes there. That's one, what's the word? Not paradigm, metaphor, I guess, for what an operating system, its main task is. It's the boss of how things get allotted as far as time and space and that kind of thing in a computer. And it also is the interface between the user and the hardware. But really, more accurately, it's the interface between the applications and the processes and the hardware. The user talks to the programs, right? Runs them, interacts with the programs, and those programs in turn need to use the monitor or the keyboard. They have to listen to the keyboard to see what's being typed. They have to know where the mouse is pointing, that kind of thing. All that's brokered by your operating system at some level. And an important thing about this too is that, and especially modern operating systems, since especially the mid-90s, maybe before, depending on the computer. In the Windows world, it would be the mid-90s, like around when Windows 95 came out. This whole idea of protected memory, because there were computers in the past, especially consumer-grade ones, where memory wasn't well protected or protected at all, and one program or process could override the memory of another and make it crash. That's why you had crashes way more often in the past. And now with, what's the word? Something bit. User bit, system bit, whatever. I'm trying to remember, there's the exact term, but there's actual hardware that helps protect things built in that is used. The operating system can make it to where one thing's protected from another thing, and everything in the system can be protected from like user applications. So privileges and that sort of thing. This is why you have to have administrators, right? They can do more to the system. So if you need to, like, for example, listen to the keyboard, you have to make what's called a system call. And that means I want to go to the operating system and ask it to use this channel to listen to this thing, like some input from the keyboard, for example. That's the main job of the operating system. But you can just think of the operating system as also like all the stuff that's running on your computer that makes sure your computer is usable, right? And that programs can run on that computer. All right. So, and in this whole graph, I didn't even talk about this, but this is showing, you got a user interface that's then an API. We'll talk more about these things soon. The kernel, especially, I'll have a little lecture on that. Hardware drivers okay. So your hardware has a certain configuration of circuitry, and it understands certain signals. Drivers are the software that translates from one particular operating system, say Linux or Mac or Windows, the instructions that it wants to send to the device. Hardware driver is what translates those signals into a language that particular hardware device can understand. So, like, I need you to write some bytes to this sector of the disk. The driver will take Windows saying, I want to write a file, and translate that into these bytes go to this part of the disk on this sector or whatever. It's kind of like C3PO, the binary language of load lifters and evaporators and all that. That's kind of like, that's really talking about hardware drivers there. So if you buy a device, like in the early days of Linux, it's less common now, but in the early days, often you would buy, like, say, a webcam or something, and it wouldn't work on the Linux computer because nobody had written a driver for it. And there's a whole segment in the reading about licensing and open source and all that where this is involved. Now, most things are even like manufactured by the manufacturer with running in Linux in mind, right? So it'll come with the drivers for Linux, or there's such a big community now that the drivers will be written fairly quickly or whatever. But I know wireless cards was one back in the day. I had a wireless card with monitor mode, and you could get different drivers that would be able to do different things. Some of the drivers might have ignored parts of the hardware. The other ones said, hey, there's this thing, like you could put one of the wireless cards I have in something called monitor mode, which turned it into it would just listen to all the wireless signals without connecting, so you could like eavesdrop with it. If you guys remember war driving, I don't know if you know that term, but back in the day when you could go around with a laptop and a wireless card and just see where all the signals were of the different Wi-Fi points back in the early days when not everybody had one. All right, going on. So the kernel, KERNEL, has different definitions. One, it's the heart of the operating system. Remember this definition because I know this is on the test, and there will be an exam, by the way, and this is buried deep in here, and I'll make announcements about this later, so it's not like you missed it if you didn't watch the video. But I will do this if I've looked at the exam, and if I remember something from the exam, I will point out that it's on the exam. So knowing what the kernel is on the exam, so make sure you make a note. And my favorite definition, which is not here, and I don't think it's in the writing, in the reading, and it's another one of those things that like that what I just told you about the broker for operating system. I think it's a very elegant definition of a kernel, and I think it's mostly right, not 100%, but the kernel is that part of the operating system that's always resident in memory. Maybe a more accurate way to say it is that in order for your computer to run, in order for it to have an operating system, you have to have at least part of the kernel running in memory at all times. Not every aspect of your operating system has to be running at all times, but the kernel does. Some part of the kernel, the main part of the kernel does anyway. So the kernel is that part of the operating system. It is the heart, but it's the thing that's resident in memory at all times. Really, the only exception I can think of to this, what I'm saying, is that there are these things, the device drivers that we were just talking about are sometimes considered part of the kernel. And say Linux, for example, they're hot swappable. And what I mean is that you can have a driver in your operating system, like on disk, for Linux stored. And then when you plug in the wireless card, for example, it will load that module into the kernel so that you can talk to that wireless card. You could say the module that mod is still part of the kernel, even though it's not memory at all time. But the most basic parts of the kernel are always in memory once the operating system is started. You have some boot process that's ROM related, right? Read-only memory that's always there on your disk drive and stuff, and in your BIOS of your computer. It bootstraps the kernel into memory. And from then on, you've got the kernel at all times, and then you might have other things that you consider part of the operating system. For example, in Linux, when you have a GUI, you have several layers of this thing, starting with X window. On top of that, you might have something called a window manager, and then on top of that, you have a desktop environment, sometimes it's called. So, especially in the old days, you'd have X window, then you would load a program into memory called a window manager. One of them was called Favorite Window Manager, FVWM. There's several other ones. And that might sometimes be packaged in with something called a desktop environment. So it'd be like KDE as an example of a desktop environment, or a GNOME desktop environment. It is pronounced that way, by the way. GNU, GNOME, the G's pronounced. Just like GIF is GIF. But anyway, so these things are considered, this is where I'm talking about the blurry line, is your window manager that's not always in memory, that just gives a certain flavor to what your windows look like. Is that part of the operating system? I would say I would put it down on the side of the operating system, because once you load it in, several different programs can use it, and anything that opens up a window, the window would look like what it looks like in that window manager. So technically, it's not the kernel. It's not part of the kernel, but it's something that you could consider as being part of the operating system. So whenever you need to have a window, it looks like that. All right. So this part where it says regulates other programs, by the way, that looks like that sense of broker that I was using. All right, so, and again, I talked about a lot of these things. So like how much time you get on the CPU, and storing files, let's see, how memory's managed. So what that means is sometimes if the size of a program is bigger than the amount of memory you have to run it, you will load only the pieces of memory for the program that you need at that moment to be running, and the rest are on disk, and you can swap them out. That's something the operating system would do. It would do that swapping out. It's called paging, because the memory comes in chunks called pages. So you load a page of memory in it that has a page of the program into memory that has the instructions you need on that page. So let's say you need instructions 200 through 215, and the size of your page would be like 100 through 500. You would load that whole page in with the parts you need, and that part will be in memory, and you execute those. And then you need to execute something that's not loaded in memory. So what do? The operating system will be paged, create something called a page fault is generated, and that will give instructions to the operating system to say to go find this on disk and for this program, and load the page into memory that I need. The instruction that I need is in. And ideally, you'll have memory big enough these days to where you don't have that happening, because that slows things down. But that's what virtual memory is, if anybody asks you. I think it's covered in this chapter, so make a note of that. All right, so common hardware. So yeah, anything where you're like working with your hardware, so getting the input from the keyboard, that's the operating system needs to do that at some level, right? You'll have a keyboard buffer that's read into memory and blah blah blah. So I did say I'd try to speed this up a little bit. We're 20 minutes in, and I think you guys know the difference between command. Now, technically, this is both GUIs, right? Because this is a window that has a command prompt in the window. Back in the old days, when you just had DOS, disk operating system, and you'd have to like type WIN, I think is what it was, that would launch Windows on top of DOS. These days, DOS is not. It used to be that Windows ran on top of DOS. So DOS was really the operating system, and Windows was kind of like, is it part of the operating system or not? It's running on top of the actual operating system, but it also acts kind of like an operating system, right? Windows is between the user interacts, and the programs interact with Windows, which runs on top of DOS. These days, it's the other way around, sort of. The DOS command prompt is an application that's inside of the actual Windows operating system. So, I'm not an expert on Windows design, Microsoft, but that's at least a roughly accurate description of the way things are now. It's like they've reversed. All right, hardware independent. So, we talk about APIs here. I do have an example ready for this. There's a geocoding API in Google's Google. It's all the same, really. I mean, it's not.
Hi, how can I help?
See, it's all infiltrated our lives now. Shut up, Google. Shut up. This is
I don't understand.
Google. Shut up. Actually, I have to say, hey, Google, shut up. But now it's going to listen to me again. So Google Maps, there is something called API, Applications Programming Interface. And what that is just one way to think of it is like functions. So you've got function calls you can make, and then the API tells you what you have to send to make some task happen. And it tells you how to like receive the results. In general speaking, that's kind of how an API works. So it's a way for you to write programs that talk to other programs. So your operating system will have an API. For example, the window manager I was talking about earlier. If you were writing a program for a Linux computer that was running, say, favorite window manager, or let's just make it simple and say KDE or GNOME desktop environment, you would need to know the API for creating a window and putting stuff in that window. That's the API. So it's a way your program wouldn't need to be coded to talk to another program to make it do something. So in this case, this is showing you the API for doing like locations versus coordinates, I think, longitude, latitude. I have actually not tried this out. So let's see. Query, click the map to reverse okay, I see. So you would put in like a place name, I think. I've not done this, so this might be incorrect. But Pellissippi State Community College, and see what happens when you click geocode. So yeah, there you go. So that will return in some way an XML or JSON. This is the output from the function. I don't know why it says request denied there, but let's see what the XML is. Okay, so like I'm looking at this the incorrect way probably, but it's a way of like one program talk to another program. XML, by the way, is extensible markup language, and also JSON's similar. It's a different format, but it's ways of storing data in a human readable but also computer readable at the same time format. And we'll probably talk about that kind of stuff later. It's not the best example, but I think you get the idea. And then you can like click on the map and it'll tell you what the coordinates are. See, this is the output here. Like this is saying that each thing I click is a different coordinates, and that's what it looks like on the map. Anyway, I think you get the idea of what API is, roughly speaking. And so again, the API will also be built into, say, Windows. Windows operating system will have an API that the programmers who write programs that run on Windows need to know what that API is. Hardware independence. Now, they don't really say anything about what this means, but one example off the top of my head would be something like Java. And I don't want to get too much into the woods on Java. Some of you might be taking a Java course right now, and you should learn this. But and C# the same way, roughly speaking. What they do, it allows for you to write a program once and compile it once, and then it can run on all kinds of different hardware. And the way it does that is you'll have, in the case of Java, you have something called the Java Virtual Machine. You download and install this program that runs on Windows, the virtual machine for Windows. And that means you can write Java programs that will run on Windows. They actually run on a fake computer on top of the real computer. And that allows you to write a Java program once, take the code for it, And you can take the same code that you compile in Java to a Linux virtual machine running on Linux, and it will also run. Not 100% of the time, frankly, but like simple programs especially, you can just like do that. This is in the early days of if you remember applets. I don't know how many guys remember applets, but you would have basically an API built into your browser that would talk to the virtual machine on your computer, and you would download code from the web it didn't matter which kind of computer it was created on. You could download that code, and as long as you had the plugin for the virtual machine for Java, you could run Java applets. Now, there was a security problem because in order to do that, you would have to have access to the actual operating system, and that's why Java itself is not an insecure language. It's just another programming language like C or C++ or whatever. I mean, the syntax is very similar. There are differences in how, like I was just saying, in the way they're compiled and run. But the thing that was the problem was the plugin. It's that gave any kind of programming language access to your computer. If you give it doesn't have, not Java necessarily. It could have been anything that had a plugin. It's just the way things had to run. Nowadays, you have JavaScript engines built in to do a lot of stuff that Java used to do, and other solutions. But so that's kind of gone by the wayside. But that in the early days, by the way, JavaScript is not the same thing as Java. Just a quick note: they have similar names. And they look a lot the same. The syntax is inspired both of them by C, but they are not the same thing, like at all. They're not related at a basic level. Even though they're both using the web at one time and they both have Java in the name. Just people use those words interchangeably. Like, I use Java to do this when they mean JavaScript. Just be aware as an IT professional that there is a difference between the two. And you will talk to IT professionals that don't understand this even. They might even use it. They might know more about JavaScript than I will ever know and still call it Java. It's a weird phenomenon, but anyway. All right. And I already talked about memory management. I told you enough about virtual memory and paging to sort of make sense. Really quick, multi-user, whatever. I want to talk about one in particular here, multi-threading. It's an interesting thing. So you've got one program, but a multi-threaded program allows you to you've got that one program in memory, but different instructions in the program can be running sort of at the same time. And it's that illusion thing, juggling. The difference between multiprocessor and multi-threaded is that in one case you got one process with different points of execution that are running in the same time. It's like there's different, if you imagine a list of instructions and one's highlighted in red and one's highlighted in green, one's in blue, there are different places. You could have many threads working at the same time inside of one document. And the example they give here is, they don't really show the example until later, I think, but you could have something that is reading input from the user, like what they're typing, but at the same time, another part of it is listening for a new connection, like a chat program as an example. So there's a different part of the same program that has a thread listening for signals coming and messages being sent from somebody else, and then another thread is listening to the keyboard buffer. So that's multi-threading. The difference, you can do this with multiple processes too. The difference is that multi-threading, you share the same memory space, and if you have if you got multiple processes of the same programming at the same time, they're executing in different memory spaces, so they don't share memory. So multiple threads are more efficient and they run quicker, but at the same time, because they share memory, you have to be very careful. As a programmer, you have to learn techniques about making sure that one thread is not messing with memory the other thread's messing with. So another example of a multi-threaded program would be one that writes to data to a file, and the other thread is reading from that file. Or maybe there's two threads writing to the same file too. When one thread's there working, the other one has to be locked out, and there's this whole process to it. If you ever get far enough in the program, you'll learn about multi-threading. It's kind of a headache, but it's also kind of fun anyway. All right, network capability. We'll talk about network. I think there's a whole section on networks in this class, so you just have to know that what a network is. It's just a way for one computer to talk to another computer, right? So, and you guys have probably grown up with networks, so I won't belabor that too much. Shoot, there's 90 something slides, and we're on 57. Also, other tasks that the operating system, they have to manage files, how they're written or read from and written to disk. Operating system determines, which which process gets the write to the disk drive at what time versus another one that might be trying to write to the disk drive at the same time. So that's where the broker thing comes in again. I'm just going to leave this for you. This is more like consumer level stuff, but I guess it's talking about the different levels and what you would use at the different levels typically, right? You could have a Windows server on your desktop. It might be overpowered, but you notice that Linux and Unix are kind of like spread out across the whole thing. Because Unix was originally meant to be a multi-user, multi-processor like server, and that, again, the dumb terminals I was talking about before, the thin clients, that's originally what it was, and then it got to where everybody could have one of those on their desktop. So, like, where's the line between the two? It's kind of weird. Kind of hard to, it's blurred. All right. I'm actually going to skip over a lot of this stuff. This is like, again, consumer information. I really wanted to focus on the design of operating systems and the tasks and and the software and the purposes of that more technical stuff. So this is more like, kind of like you could read this in a consumer magazine or whatever. Though I do want to talk about Linux. Linux is an open source, what's the word I want? Not adaptation. Emulation. I guess it's emulation of Unix. So this, I don't want to tell the whole story of Linux. It's based on a guy named Linus Torvalds. He's Finnish. His name is Linus. So that's how you pronounce Linux, right? So there's people argue about Linux versus Linux. There's a case you can make for if you pronounce his name as Linus, like you would in English, right? You could say that it should be called Linux, right? It sounds horrible to me. I know there's somebody in the class who does. I don't want to call you out or pick on you, but I'm just going to say the accepted pronunciation by most people is Linux, which is actually neither name, right? It's because it's not Linux, but whatever. You get the idea. So what he worked on a computer called Minix, like I think it was a French computer similar to Unix, small scale kind of thing, and he wrote an emulator for the key thing is that it was for the 386 chip, the PC processor. Unix often worked on different kinds of processors, like there's Sun Microsystems Spark, and there's different processors. But the one that you would have in your computer, your PC at home would be Intel, the 386, 486. So he rewrote an operating system to work on that chip. This is the whole device driver. You can kind of think of it this way. It's like an operating system is a meta device driver that has to understand how the processor works, the language that the processor speaks. When I say the way the circuits are laid out of that processor, the API for that processor, you have to write your operating system kernel, the kernel in particular, to talk to that hardware. So Linus Torvalds wrote, but what it came down to is he wrote Unix to work on a PC, which hadn't been done before. You had special hardware that Unix that ran on. So that's what Linux became. And he wrote it in such a way to where like all the commands and stuff were very, if not identical, like very, very, very close to identical. There's different kinds of Unices, is what they say it in the world, and flavors of that. And there's lots of different flavors of Linux. There's also open source adaptations of emulations of Unix that are not called Linux, like FreeBSD. Berkeley is a Berkeley version of this, so there's a lot of blur here too, but that's what Linux is. Linux was originally it's a hacker project, basically a fun project to get a Unix at home on your desktop. But then that turned out to be a very useful thing, right? The whole open source about it, where people can cooperate together freely and nobody's worried about not plagiarism, but copyright, right? And also, like, it would work on all this low cost hardware because Unix computer hardware was very expensive if you wanted to buy some microsystems. And there were different ones, I guess, I don't even know who made all the, I want to say Xerox made some. The mouse, for example, was invented at Xerox. I'm sure IBM had some Unices, and the ones I'm familiar with were Sun Microsystems. But anyway, I think you get the idea. Is that it's a very powerful operating system that was written to work on low-cost hardware and also open source so that people could cooperate. It took off. All right. So there's a bit about Linux and Google Chrome again. This is like basically if you need to really use Google Chrome books, that kind of thing, you need to have like a Google account and Google Cloud stuff. That's the whole point of that. So you don't need a powerful computer. It's less expensive. But the drawback is you need like that connection to the web for it to really be useful. To Google stuff too, to be useful. All right.
I found a list on the website that beacons.
Hey Google, shut up. I hope this is amusing for anybody who actually listens to these or watches these videos. But anyway, of course, so you've got the like within the past decade or so, you've got the whole smartphone thing where you basically have computers in your pocket. It's kind of hard to imagine, even for me, when I first started getting online before the World Wide Web. Shortly before it, I was on Usenet news groups and FTP and Archie, Veronica, and what's the one for the library documents? I use Veronica to search it. I can't think of it off the top of my head. G starts with G. Anyway, I'll remember it in a minute. Oh, Gopher, and IRC and all that kind of stuff. That's where I started my online life, really. The World Wide Web came out a couple of years after I started doing that, and that's when things started to take off, especially when I opened it up to the corporate world in like 1994. Because I don't know if you guys know this, but it wasn't always commercial, the internet. It was originally a military / university cooperation, the ARPANET. What's the the Advanced Research Projects or something, or for the Army or whatever. It was a military project. It was meant to be a network that could survive nuclear attack. If parts of it went down, the other parts would not go down too. That was the whole original purpose, and then it started to be used as cooperative, like exchange of information between universities and stuff. And then, over time, it became what it is today. So that's the whole my private company is kind of BS in my opinion, because it's all built on top of TCP/IP protocol, which was developed by our tax money. Never mind Section 230, which is also government protection of somebody. You don't have a right to liability protection, so maybe you need to give that up if you're not going to let us have free speech. The end of political rant. But anyway, it's not just as simple as the First Amendment doesn't cover private companies, though, when they're all entangled up with government taxpayer money. They're built on top of it. Twitter didn't invent the internet. They wouldn't have taken that well, it didn't exist, obviously, but private companies did not create the internet. They just exploit it today. Anyway, so yeah, Google Android. So the thing I want to say about that, as far as how this relates to operating systems, is that you'll see a little section on embedded operating systems later. These are little mini operating systems that are special purpose for specific purposes that are built into like hardware. So that's kind of inaccurate when you think about smartphones, though, because smartphones are multi-purpose devices. That's why they're so useful, right? But the special purpose here is that there's a special embedded version of Linux that Android phones run. And there's a special embedded version of Linux / Unix, like kind of iOS is basically these days also an emulation of Unix that runs, I guess, on iPhone. I'm not an iPhone person, so I'm not really intimately familiar. I've developed apps on Android, though, so I know a bit about that. So Android's a special form of Linux, and you can use an API that usually uses Java programs to talk through the API to the smartphone to create applications on the smartphone. This is how Android works. So that's where this that's all you really need to know about embedded systems from what I'm going to say. Again, read all this stuff on your own, but I wanted to emphasize that thing about Android just now and skip over the rest of this. So, and this is more about the middleware, about the where is the line between the operating system program or process and just like something like Word, like a definitely end user thing. So some of the maintenance stuff you would use, if you look at what is it called? Server. Wait, I'm trying to remember what you type in the run bar. Just system configuration and maintenance stuff in your computer you could consider to be sort of in between operating system and end user applications. All right, and I guess that's where they're using middleware to describe that. All right, so this is on the test, so I remember seeing this. Proprietary software, that's one of a kind program for a specific application. So proprietary, I'm trying to remember the etymology for it means ownership, basically. So the proprietor of a bar, right, is the owner of the bar. So proprietary here is the program is owned by the company. It was designed for and bought for and owned for and run by that company for a specific purpose. And again, an owner or a proprietor is where that comes from. So always make sure you remember that. Like if it's a proprietary software that does the personnel maintenance for a company, that does like the time cards and the salary and benefits and all that stuff for that particular company, for like say Coca-Cola, you couldn't, that means AT&T can't use it. They would have to like reinvent the wheel. They couldn't just take that program that does personnel for Coca-Cola and use it at their company, at Home Depot or whatever, at a different company to do the personnel management, the employee management, right? As opposed to, say, an example of off the shelf would be something like QuickBooks. So just about any company can buy QuickBooks and adapt it. I mean, it's the same software for all of them, and they probably have to do specific, adaptations of it, like configurations of it to make it work for their purposes. But it wasn't developed. QuickBooks was not developed for one company. It wasn't developed for company X to do task X at that company. It was developed to do like general like accounting of funds and stuff, but also I think it bled over. I originally remember it as like a personal accounting kind of thing, or maybe a small business accounting where you could like do your debits and credits for buying things and selling things or whatever. I don't even know because I'm not a business person, but in the later time it seemed like it was also extended to cover more like employee stuff. So I know like one company I work for, they use QuickBooks to do my paycheck. So anyway, you get the idea. So that's the difference between two. One's mass produced, the one is specifically designed for a particular owner. Don't confuse the two on the test. Anything else? I've got 20 something more slides to see if it's important stuff. I would let you guys look at this software as service, and this is stuff like, we're doing orders between companies and that kind of thing. SAP, not my strong suit. I don't feel like I'm qualified to really preach on it. Your instructor, none of your instructors know everything. So just like SAA and SAP and all that, I know it was used at the last company I used, but that's more the business side. I was doing the support for the project managers. SAP would be, if I remember right, I might be wrong on this, but if I remember right, it's how you like create orders for products and pay it and stuff. I don't even know. It's transmit the money around. I don't know. I'm sure my friend who's an accountant, he probably knows all about it. So these are like some typical end user stuff, which you guys are probably already familiar with. So, right, Word, Excel, Access. If you're talking about like, if you just stick within the Office suite, right? PowerPoint, That's kind of like examples there. And they've got some categories of like, personal productivity. So I'm just going to speed through this. You guys probably know more about mobile application software, like what that can be used for, because you use it all the time. I see you walking around campus with your face in your phone. I'm not going to get out of your way. You need to look up. But anyway, I have a phone. I carry it with me everywhere, but I'm not always looking at it. They are very useful, but look up and enjoy the world a little bit too, guys, especially in your car. Don't drive and look at your phone, please. Don't do that. I know you think you can do it, but you're wrong. They've done millions of tests, and 1 out of 1,000 people can adequately like drive while paying any attention to their phone. And I doubt any of you are that person. So anyway, that's another rant. And so again, these are mobile applications. I don't presume to teach you about those because you probably are all experts in them. Now, programming languages, last part. This is the part I should know. Only about 10 slides. So programming languages, I don't want to compare it to real languages, though you can make some comparisons. Like, is C to Java as French is to Spanish? I don't know. I would say C is English and Java is like baby talk. No, I like Java all right, actually. I teach it. But it's just it's a framework for creating instructions that computers can understand. And it's also, you can think of a programming language as sort of the interface between a person and a computer too, in a way, because it gives you a way to write something that you can understand sort of once you learn the rules of the language, the grammar of the language, or the syntax, which is this word down here. Once you learn that, it's kind of human. Actually, I want to do this because I see that this is missing. We might talk about this again later on, but I want to show you. This is a common thing that you would learn about this point in a survey class about IT stuff when you're talking about programming languages. Let me find a good chart. Let me pause it actually. All right, this is the a fairly okay diagram for what I'm talking about. So there are these levels of sophistication or abstraction when you're talking about programming languages. And I wanted to briefly describe them. So that 1GL, it's not IGL, it's 1GL. It means first generation language is what that's abbreviation for. This is the common way of writing this in the IT world. So a first generation language is also usually known as machine language. So they just put the zeros and ones there to symbolize that, but the word you usually use for a first generation language is a machine language. And a machine language is almost like you're a machine and you're talking to another machine. So it's like R2-D2 talking to another astromech droid in their own language because they're hardware and they have, but really what it is zeros and machine language means a way of inputting into a hardware device the signals of zeros and ones that it needs to know in order to do instructions. So the machine language would be, it's kind of hard to describe this in English and you don't really need to know much more than what I'm going to tell you here, but sort of like the wiring diagram is one way of thinking about it. This wire needs to be, this input needs to be on and this one needs to be off. This one needs to be on. If you ever did dip switches on anything, that's sort of a machine language programming right there. A machine language programming also would be, if you look at the operators, not necessarily, think about old-timey operators when they plug those wires in. And that's sort of what it is. But if you go back further to ENIAC, one of the first mechanical electronic computers, I should say, you would, to program it, you would have to rewire it. You would turn dials, you would unplug those kinds of wires I was just describing, like the operator uses, and replug them into different sockets. That's how you would program the machine to do a specific calculation. And every time you had a new program, they would have teams of, and back in the World War II, it was women programmers because, you would have somebody who wrote out what the instructions were and what had to be done, and then you would have specially trained sort of sub-programmers, and they were usually women who were working in the workforce, right, because the men were fighting, and they would go and reprogram the unplug and plug in wires in certain ways and turn dials to certain things in order to run a certain program to do it, like maybe a ballistics missile calculation or something. That's one of the examples they use. I don't know if that's folklore or not, but because it was originally meant to do firing tables, is what the funding behind ENIAC was. Electronic integrator, ENIAC, electronic numerical integrator and computer, I think is what it stood for. You can look it up though. ENIAC. It's usually considered like the first really sophisticated electronic computer. Colossus also in England was at about the same time. The Tanasoff Berry computer right after. There's a like, I guess people would argue which one's the first. Maybe I think ENIAC is usually considered to be the first though. ENIAC, and you would literally rewire it to program it. That's kind of what a first generation language is. Maybe one slight step up from that. I've never actually done machine programming, so I don't know. But like writing those device drivers, you do that usually in a higher level language, but you need to understand the machine level in order to write a device driver. Assembly language is a little bit, it's a one-to-one correspondence. So if you write an instruction in assembly language, it will correspond to an instruction of zeros and ones in machine language. It's a one-to-one translation. So, but let me show you what it looks like. And each one of these things varies from computer to machine to machine. They have their own language, right? So that binary language of load lifters versus binary language of evaporators, they might be similar, but they're slightly different because they're wired differently, right? That's what machine language is. So the machine language of how a CPU in an Intel 486 is different from what the machine language that you need to understand to talk to a Sun Spark chip processor. But that's the very lowest, right at the metal, right where the rubber meets the road level of talking to a machine and programming it. And again, like a version of that you could consider to be like the rewiring of ENIAC. This is Wikipedia, of course. Wikipedia is fine for stuff like this, by the way. Don't use it in a report because it's not a primary source. But if you need to look up something quickly, you can't just say, oh, Wikipedia. I mean, if it's about politics, sure, because there's a lot of opinion there. But if it's basic facts, it's perfectly fine. So don't like overcompensate on don't hyper-react to the whole Wikipedia's dumb thing. I was just looking for something that looked like an assembly language, and when I pulled it over, it was Wikipedia. But this is kind of what it looks like. Let's see. I don't really like this example, though. What I'm more familiar with. Let's see. This is better. Like move the value that's an A1. I don't know what 1H is supposed to be, though. So that's not a great one. I need my language that I've seen before. This is not. I should have had. You know what? Pause again. All right. Is it good that I could do this stuff sort of off the top of my head, or should I prepare more? I don't know. That's the question. Like, I think I would be glad that my instructor could do that, but whatever. A little preparation couldn't hurt, so we'll see. But so this is a good example of like sort of all three levels. So this is a 3GL, third generation language. This is technically, let me look and make sure, this is C. I can tell because it's standard lib.h and the pound include, and I'm pretty sure it's C. It could be C++. They're very similar, but anyway, this is C. And I can tell you what it's doing a little bit. So there's a function called sub. You give it x and y values as parameters, and it returns x multiplied by 2, and then you add whatever y is. So for example, if this was a 2 and a 3, I don't want to make the math. I can't do arithmetic in my head. But let's say it's a 2 and a 3. So this would be 2 times 2 is 4, right? Plus 3 is 7. It would return 7 if you put a 2 here and a 3 here. Is that right? Anyway, double check my math, but you get the idea. All right, and what this is command line arguments. We won't talk about that. This is declaring a variable to store a whole number. We call that variable A, and we're saying we want A to have whatever you get when you take I'm glad I mentioned the command line arguments. Whenever you take whatever is at the position of the second thing on the command line. So if you say run, let's say the program's called foo. You would type foo 3, right? It'll take that 3. That's what argv1 is, and it'll convert it to an integer. So 3 is a byte. It's a character. It's a symbol, right? You want to convert it to the numerical bit pattern for 3. That's what A to I does. And then you return this with 3 here, and then whatever A is. Let's see. I'm sorry, not that. No, the number of arguments on the command line, which is 2. So it would be 2 and 3 again. Okay, I did that was by accident. This is showing what maybe the bit pattern. No, wait, this is not the bit pattern. This is the instructions, the order of the instructions is what this is. So this is a hexadecimal representation of each instruction. And this is showing in assembly. Say that this is instruction like this. Just think of these as line numbers. That's the easiest way to say it. Am I correct on that? Yeah, I think so. So this is a translation of what this at 3GL is and 2GL. So assembly language is 2GL, second generation language. And this is saying push, whatever, I'm trying to remember what push means. And push is like a stack. You're pushing some value in, and then you're moving this value to this location. I'm not really good at reading this particular assembly, but it looks like it's using a stack kind of construct to do some math and stuff. And the one thing I'll say here is that I understand this one. This is saying take whatever is located in, these are probably registers actually, this ESP and ABP. I had to look at the diagram for this assembly language to know what these things are actually, but I want to imagine this is some kind of memory location anyway, whether it's a register or not. And you're taking whatever value is in there and you're adding 4 to it. And then probably storing whatever you get back to this, so it'll change it. So add's very simple, right? There's different kinds, add, push, jump, branch. I'm trying to remember some from assembly. But the long and short of it, you don't have to understand all this if you're listening with your eyes wide open, like, how am I supposed to? You don't need to understand any programming right now. I'm just trying to explain what the difference is. So you notice how this looks a little bit more like English. You saw how I translated it because I know C. I could tell you what's going on, and I had trouble with this because this is more like this is what this translates. This you take this third generation language as input to a compiler, and the compiler will pop out this assembly, or maybe even go down to the machine language, depending. Usually it just goes down to machine language, but you can do the assembly. The thing about the assembly is this stuff, each one of these lines corresponds to a bunch of zeros and ones. The zeros and ones are the machine language. So if you go back to that picture, that's what's going on here. You take some Java or C or C++ or stuff that looks like that code I just showed you that I translated, and it turns into all that stuff on the right-hand side, all the push and pops and stuff. That's what that is. And then that will be translated at some point to machine language, the actual wiring inputs and outputs that the machine understands so it can execute them. Because again, the machine doesn't understand Java and C++ and all that stuff. The human programmer understands that, and that stuff will get translated in a very precise way to the lower level stuff the machine can understand. SQL, by the way, this is using databases, and if you're in my database class, which you probably aren't, but it's usually considered to be one step more abstract. This is at this level, you learn the syntax of the language to describe how the things work. Like, I need to call this function, I need to pass this parameter, I need to make this assignment. You're kind of describing what needs to be done and how it needs to be done. At this level, it's a little bit higher up, and you're saying, I need this to happen, and it figures it out for you in a way. And that sounds like really hand wavy. You'd have to see some SQL to see what I mean, but select these things from this table and exclude all these things on the last line. It's more coarse-grained instructions you're giving it to it. This is a little bit more detailed, and this is very, very detailed. These two are the same level of detail because they're one for one, but each instruction in the actual hardware, the CPU, going back to that original video of today, the ALU and control unit. This stuff these levels are what this understands, and these are closer to human. As you see, there's a progression to English, and there's higher generations, 5GL. I forget what you put there. It gets fuzzy and theoretical above 4GL. As a matter of fact, some people would put C++ and Java in 4GL. I don't agree with that, but anyway, that's enough of that. And then syntax is just the order and the words that you use, the keywords, they have to be spelled exactly right, and they have to be in a certain order. And the punctuation, the parentheses and semicolons have to be in certain places. It's the arrangement. If you look up syntax, it's the arrangement of how you put things together in English syntax. I say, I hit you. We know who's getting hit, right? If you say you hit that's bad grammar, but if you hit me, right? Bob hits Greg. We know Greg's getting hurt. Greg hits Bob. We know Bob's getting hurt. Word order is how you do meaning. The syntax of your words in English is how you do that kind of meaning. In other languages, you do it differently. You can say, Markham Brutus Pugnat. Brutus hits Mark, because the UM on the end means that's the person getting hit. So that's an example of a different kind of grammar using inflection. But syntax is just the word order is one very rough definition of it. I want to say it means together. It's almost like the same etymology of contiguous. Touching together, sin means together, and tax means touch. It's how things touch each other, the order they go in. One thing follows the next. I think. See what Edom Online says. I know this is a tangent. I said I wouldn't do this, but I think, again, if you understand the roots of words, you understand exactly what they mean in a very, together, arrange. Together, arrange. Tasein in Greek means to arrange. It's related to the word tactics. So arranging things together is what syntax means. So the way you arrange your keywords in your programming language, you have to do it in a precise way. In a 3GL like C or C++ or Java or Python, you have to do it in a certain way in order that it can be translated into something the machine can understand. And the translation's done by another program, right? So program's translating the syntax of one program into a encoding that the computer can understand and execute the instructions. And this is just a table of a bunch of different programming languages that tells you a little bit about each one. These are, again, none of these things are hard and fast rules, but they're kind of the way people think about these things. So COBOL is considered an old language you use for business purposes. It actually stands for common business oriented language. CO, common, and then business oriented language. C was actually designed to write the operating system for Unix, if I'm not mistaken on that. There was a B language, I know for sure, but C was developed, I want to say, at Bell Labs the purpose of it was to write Unix. And then it was used to write programs in Unix and then so on. And C was like, there's a whole family of languages that inherit their syntax, the way they look, the way you name the functions and stuff, the keywords, and the parentheses, the curly braces and the semicolons and all that are inherited from C, even though it's not exactly the same as C. So for example, C++, Java, C#, all these languages look like C. C++ and Java are object-oriented languages. C++ is compiled for each machine. Java is compiled once and run on different machines, on virtual machines. But otherwise, they're both object-oriented. Some people would argue that C++ isn't really object-oriented. Java was built with object orientation from the get-go. It was from the top to the bottom and sideways. It's object-oriented. C++ is just C with object-oriented ideas slapped onto it. So I'm going to say if you compare the two, Java's been optimized a whole lot over the years. C++ is usually considered to be still more hot rod fast. That's why it's used for a lot of game programming and stuff. It's very efficient on memory use and stuff. JavaScript is originally a scripting language. It's more and more at the same power as a full programming language these days, though. So a full programming language can be used to write any program. Scripting languages are usually more focused on smaller things, and they can't just do anything. But JavaScript was originally called LiveScript, and it was meant originally to do stuff on the web. When Java started being used for the web stuff too, for applets, whoever like created JavaScript, I think it was, God, who was it? Same people who do Mozilla. The guy who founded Mozilla created JavaScript, I think. It was, so let me tell you the difference between the two, besides the name. Again, there's no relationship aside from, hey, I want to name this thing Java because JavaScript because Java's popular. JavaScript was meant specifically to do some dynamic stuff on in web browsers. So the engine that would run JavaScript was built into the software of the web browser, and then you could write JavaScript that the web browser little engine, JavaScript engine, would understand and do neat things, right? Java was meant to be, the earliest reason that you had Java was to write programs that would work on just about any kind of hardware, not just computers, but say, for example, if you have, I know there's a Blu-ray player I had that the menu and stuff and all that was written in Java. That was the original purpose. And then like when the World Wide Web was becoming popular in web browsers, they found out they could use Java to do applets, because the whole point of Java is that it will run on any hardware. So if you download the code and you have the applet in the Java virtual machine, you could run anything you saw on any website, right? So that's kind of what it became known for a while, but now it's back to be running on all kinds of different hardware, including phones, for instance. So, a lot of the programs you have on your smartphone, and Android anyway, was written in Java. But also like offerings, like I was saying, for a Blu-ray player or like little devices will often have Java. You'll see it say Java inside because Java was used to write that stuff. PHP is sort of like JavaScript. I won't get into it. Python was originally also a scripting language. It's very powerful now, and what it says here, it's not fully covering what it does, because the main thing that it's used for, because of all the development, and it's integrated with some C libraries too, some stuff like NumPy for mathematical purposes. It's used for AI machine learning stuff. That's like the huge thing that Python's used for now. So if you really want to get into machine learning and artificial intelligence and that stuff, Python is like the main language you want to like start with. There are other ones, of course. You can do AI with any language, really, but Python has a lot of work that's been done for utilities that will help you do machine learning type stuff. I know, like in the classes I've had, I did one where you wrote programs to try to predict the stock market with machine learning. We did all that in Python. And Ruby is some kind of, I never got into Ruby, so I'm not sure. It's like some web thing. So I guess mobile apps too. And SQL, again, SQL is a 4th generation language it's specifically used to talk to what are known as relational databases. And we'll talk more about that later, I'm sure. But just keep that filed away. It's a way of writing instructions that relational databases can understand, mainly for like retrieving information queries, but also for creating tables and creating views and what am I forgetting? Inserting data, deleting data, dropping tables, updating data. SQL is used for that, specifically for relational type databases, which are most of the ones you've heard of, like Access, MySQL, SQL Server, Oracle. Most of the Oracle things, those are all SQL. They understand SQL. We won't talk about the bugs and stuff because, frankly, it's boring. It's important, but it's boring. So I'll leave that for you. And this video is already too long. Copyrights and licenses. The main thing you want to be aware of is what open source is versus not open source. So let me give you just like, without harping on this too much, I want to talk about these two expressions. Look them up and compare them to what you read in this material. Free beer versus free speech. So a lot of the open source software and stuff that's in the GNU license these things are sometimes both free beer and free speech. So like you can usually get Linux for free if you want. You can download it off the interwebs onto some kind of thumb drive or something, or burn it onto a DVD-ROM and install it on your computer, and you didn't pay any money except for what you need, to be on the internet or whatever. You didn't pay somebody to download the Linux. And it's also free in the sense that you can go in and make changes to it without having to get permission from somebody to do it. The only permission you need is in the license sometimes. So for some of these, I'm trying to remember what it's called, the GPL, the General Product License or whatever. The thing you agree to is that if you create stuff with that license, you also have to make other people able to copy your source code with that license also in it. So the license it's like paid forward. I'm not a lawyer, so look at that. I know you can create software that people have. It's not free beer with a GPL. They pay you for the software, but you have to include the GPL license in it, which says that if somebody else, at least those portions of the program have to be open for somebody else to copy and then add on to if they want, and incorporate into their programs and so on. So it's like a pay it forward kind of thing. That might be a slightly inaccurate description of GPL, but you get the general sense of it. And that's the free speech side of it. I'm not talking about literally. I'm talking about metaphor. So free speech means liberty, right? Not out of jail. There's another way of thinking. The not in jail license. You're not in prison. You're not constricted. That's the, in quotes, free speech version of free. And then the free beer version of free is you don't have to pay money for it. So it's obviously true that you have to spend a whole lot of money for Red Hat. Red Hat. It used to be Red Hat was not like that, actually. You would pay for it. You would buy the disk and install it, and so it wasn't free beer, but it wasn't very expensive. But these days, Red Hat's divided up into two versions. You've got Fedora, which is the home user thing. You often don't have to pay to install Fedora. But if you buy Red Hat, it's enterprise level operating system software, and it comes with management, right? You support and help, and like you pay somebody to run your Red Hat stuff and support you on it. All right. So I think that covers everything, and that's I don't know if all the lectures are going to be that long. This is stuff that I like talking about, so I don't want to scare you. I do go on tangents. I think the tangents are important sometimes, though. So bear with me. Maybe fast forward. Sometimes I might have gone over stuff fast. You can rewind, right? I know this is 2 hours. They're taking up your time. I'm taking even more time right now. So I'll try to tie this up. But yeah, so bear with me on the lectures and use them however they're useful to you. But what their purpose is meant to do is for me to help guide you and supplement you and call attention to aspects of the stuff that you're learning that might not be strictly covered in this. You can read this all day, right? I want to call attention to things and put things in a different way to help you understand it. All right, with that, I'll see you in the next video. Bye-bye.